Okay, so thanks for joining me today. My name is Ben Zillow. I'm just going to do a quick video on some points that I generated for just another company I was working with a little while ago, and I figured might as well share this a bit more broadly. So what I'm going to be talking about today is 10 rules of scaling. So to set some clarity on this right at the start, I'm not going to be talking about so much scaling teams or scaling companies, though I might talk about that stuff in the future. Today, I'm going to be talking about just the scaling the technology for web applications. So if you're not interested in that, feel free to bail out to hurt my feelings. If you are interested in that, stick around. A few other important call outs. One is that, like most things in technologies, these are really more guidelines than rules. Of course, every situation and context is different. And speaking to that a little bit, this is more written to the context of traditional architecture web applications. So in particular, kind of traditional centralized database, SQL database, Postgres, MySQL, Oracle database, and web server architecture. Lots of this can still translate to modern architectures like more serverless architectures or something that's more Dockerized, Kubernetes based, those types of architectures. But of course, some of the points that I might make might be a bit less relevant. So having gotten all that boilerplate out of the way, let's dig into the first rule. So rule number one, the scaling limits you'll hit next aren't the ones you're expecting to hit. So this has happened to me a number of times where you've got some kind of, scaling issue that you're watching. So let's say this is like disk size on a server. So you know that you're going to hit this line eventually. You're kind of watching it slowly trend up. You're anticipating that you're going to hit this problem. And what seems to happen time and time again is that something comes out of completely left field and just hits you in the face way earlier than you're expecting to hit the issue. So the key idea for this is, first of all, don't lull yourself into a false sense of security because you're watching the things that you think are going to hit scaling limits and projecting, oh, we're not going to have issues. We don't need an infrastructure team for 6 months because we're not going to hit scaling issues. There's a tendency that something you're not anticipating, something you're not expecting. It could be an API limit on an API you're using that you don't know about. Even issues I hit with like S3 and the scaling limits of S3, you're thinking S3 is infinitely scalable, but that's actually not true. There are scaling issues you hit in a system like that. So don't get overconfident, and all the more reason to have monitoring in place, to be thinking proactively about what issues might happen, to have good war games in place for dealing with hitting the scaling issue you don't anticipate. And all that plays into rule number two, which is that scaling issues can take a really long time to fix. So unlike most bugs in software architectures, even if you have found out exactly what the issue is, sometimes the solution could be months off. It could be months worth of engineering work. It could be just the actual transition to new infrastructure. Maybe the issue is you need to get off of your current hosting provider, move to another hosting provider, and the search process of figuring who that's going to be, signing the contracts, etc., could easily take months. So this is a really painful place to be if you've hit a scaling wall that might take months to fix and there's nothing you can do about it. Personally, I have been in that place in my career where you're running into things like daily outages due to the load on your systems, and there's no quick fix answer. Sometimes you can find some band-aids to buy you time, and we'll talk about that a little bit more. But other times, you're just going to be in a world of pain for months. So what do we do about that? Well, one of the best things you can do is have proactive monitoring of your systems, looking for the leading indicators that to look for. Again, you're not always going to anticipate what the problem is going to be. Some of these are more predictable, things like disk space on a database server, things like CPU time, CPU load on your web servers. Some of these things you can have proactive monitoring for. And when you cross your warning, do something about it now. That's the other thing is even when you see, again, going back to the previous point, if you see something that's going to be coming and you're overconfident about your ability to fix in a certain period of time, or not needing to fix it for a while, it can easily get you into a world of pain for an extended period of time. Rule number 3. So again, this is starting to talk a little bit more to what you can do about it. Often scaling issues can be mitigated or delayed by vertical scaling. And what I mean by vertical scaling is generally a larger server, a bigger database server, a bigger web server. These things will basically, what allows you to do is have your system continue to behave exactly the same way it's behaved, not need to fix anything, not need to make any architectural changes, just get more time until your current systems, your current structures, your current architecture is going to become a problem. But it rarely fixes the problem. Like if your database has hit a limit and you upgrade that database, how much time is that going to buy you? Like one question is, how fast is your customer base growing? But if you have a large base of historical data, your database size could actually be growing in some kind of exponential factor faster than your user base is growing, especially if you've got network effects and other things where more users on your system will inherently drive more activity. So while vertical scaling might buy you time and avoid downtimes, get your users enabled, those are all good things. The right time to really fix the issue is as soon as you bought yourself more time. This kind of goes back to the same thing I've been saying, but if you upgrade your database to buy yourself time until you're going to have to actually fix issues with, maybe how your systems are architected, and then you go, oh, well, now we've got 6 months, because last time when we did this, it bought us 6 months. You might not have those 6 months. So the right time to do it is when the pain is fresh. From kind of a project management standpoint, that'll often be the best time to make the case about why it's important to do too, when sales has been getting complaints, success has been getting complaints about how much it sucks to have downtime. Take advantage of that felt pain to advocate for fixing the thing properly as soon as you've bought that time. Don't wait. And then not all scaling issues, but a lot of scaling issues can be solved by horizontal scaling. So if you're talking about something like modern serverless architectures, that's effectively what you're doing, is you're throwing out web applications and replacing that kind of architecture with an architecture that scores horizontally in terms of however many threads of compute you need, you just kind of get. So you don't need to worry about actual units of servers. So that's a really good solution. It often comes with additional complexity. Sometimes it actually involves a change in technology from one database engine to a different database engine that has better horizontal scalability. Sharding can be part of that, though sharding is often a very expensive and complicated process. That's not a silver bullet either. But in terms of thinking about things, if you're solving a scaling problem using vertical scaling, a bigger server or something like that, you probably haven't actually solved it. And as a first place to look for solutions, you can think to horizontally scalable solutions. The punishment for not having enough memory to have database work inside of memory is significant. So this one's a little bit more specific to traditional databases, something like Google. Their big table stuff is very different. Might not have these same challenges. I haven't personally worked with those types of systems at scale. But speaking more specifically, things like Postgres, MySQL databases, even things like, God, I'm blanking on it, but no SQL databases. The issue, I didn't understand how important this was. In some ways, it's kind of intuitive. Basically, what's going on is you've got your database server, and it's got so much memory. And then anytime it doesn't have something already in memory, it needs to go and fetch it from disk. It needs to pull that data in from disk. And also, of course, it needs to write things back to disk to commit them at some point. But that can be delayed in some cases, depends on the database. But in particular, these fetches from disks. And these can be really expensive. In some cases, these can be global locks. Ideally, they shouldn't be. Hopefully, they're only page locks or table locks. But it can really slow down your database and create a lot of locks that are blocking other operations from happening in your database every time it has to go and fetch memory from disk. So there's a few things that can lead to this. One thing is if you've got a long history of data and you're constantly doing operations on that long history of data. So something like a calendar system where you're generating analytics on all the history of the calendar, and it goes back for decades of data. So you've got a long tail of data, but the old data isn't just stale. You're continuing to have to reload that to the database. You know, in particular, very hot tables where you're changing a lot of the data in the entire table on a regular basis. These things can make it so that you've got a large database, and a lot of that database is being interacted with all the time. Conversely, if you've got a very large data set, but the working set, the part that you're actually interacting with, is only kind of a thin slice of it, you know, some more recent data, something like that, then it can be okay. But it's definitely something to watch, and it's something that I underestimated in my career, is how significant the performance drop off can be once you start to cross this edge. And it's one of these things that can be a performance cliff. You don't know you're about to hit it because all your performance metrics are looking fine if you're not specifically watching for this until you hit this cliff. And then the more that it needs to fetch data from disk, that becomes an exponential cliff because it's pushing other stuff out of disk to fetch that stuff, I mean, out of memory to fetch that new stuff, and then it's going to have to go fetch that old stuff again as well. So just appreciate how important it is to try and have enough memory to have your working set in memory and figure out what that means. One small caveat on this one to watch out for as well is indexes in a lot of databases are always in memory. So if you're trying to fix your database performance by throwing more and more indexes at it, what you can actually be doing is reducing the amount of memory that's available for the actual working set of data. So be wary of that path. So that's somewhat related to this idea of don't fix the issue at the wrong level because you don't have visibility at the right level. So I'll talk to a specific case where I was looking at New Relic metrics, and what I was seeing was active record time. So for a given request, you know, say the request took 500 milliseconds to respond, and I could see that 300 milliseconds of that was being spent in active record. So the immediate intuitive inference is to say, oh, the query took 300 milliseconds to happen. But in reality, what was actually going on is that the query time was much smaller. You know, the query time might have been something like 50 milliseconds. But in active record, there were other things going on. So in this case, what was actually happening is that there wasn't enough connections in the connection pool. So active record had to wait for a connection to become available. And that's what that 250 milliseconds was. So like if you look at this active record metric, and you don't have visibility deeper down, and you assume, oh, my queries are slow, you could spend a ton of effort and energy trying to, you know, make your queries faster and see no improvement in your request times. And it's because the monitoring was at the wrong level. This is really tough. It's often a whole suite of different tools that you need to get visibility at all these different levels. And then to figure out, you know, where the issue is actually happening can be really challenging. Other examples of this is seeing slow requests and thinking, again, it could be something like database query times, or maybe your web server is slow. And then what it turns out is it's actually just a large payload over a slow connection. You know, one of your customers is on a really slow cellular connection. Well, it's going to tie up that server connection until it can actually send all that data. So that can show up as a very slow request in your web server metrics, again, depending on which level you're looking at those metrics. So just be careful about making assumptions when you see things in higher level metrics, because there might be other components in that time that you're not aware of. Make your slow queries fast. So this is another thing that I had heard and just didn't really appreciate is I would think, you know, okay, I've got 10,000 queries in this database. I've got some slow queries, but they only make up a couple percentage of the overall, you know, query time being sent to this database. They're not important. This will relate to another idea that I'm going to talk about in a second about homogeneity of your load. But in addition to that, when queries are slow, there's usually something wrong going on. There's not very many queries that if your indexes are proper, the query plan is working properly, you've got the working set available, are going to be slow. especially not if you're talking about typical web application activity, you know, not some big reporting query or something like that. They shouldn't be slow. And if they're slow, there's a good chance that your database is getting locked, that there's, you know, page fetching going on, that there's other things going on that are actually going to have greater negative impacts just beyond those queries themselves being slow. So especially if you start to see database scaling problems, go look at your slow queries. It's often one of the most readily available forms of database logging. It's just like slow query logging, so you can probably get it pretty easily, and start fixing those things. Even if they're not directly related to where you think you have issues in scaling your database, go find your slow queries, try and make them fast. So super related to that last point. Don't assume the query planner is smart. I've been amazed as I got into more aggressive database scaling problems, how often the query planner was doing something really dumb. One of the reasons for this is that your table stats might not be up to date. So this is something I'm most familiar with in the context of Postgres, but would apply to other databases in their own ways, depending on how they use table stats to generate query plans. But basically, the database keeps some high-level approximate statistics about the distribution of data, size of data, and it uses those statistics when it's trying to figure out how to actually execute a given query against the database. So if you don't know this, you might write SQL, but how that's actually going to get processed by the database and how the database is going to search through its data to find the results is up to the database. So the SQL is just saying, give me this stuff. It's not actually telling the database how to do that thing that you've asked for. And in theory, you can do something like create an index to make a query fast, and then the database query planner might just decide not to use that index. And again, that could be because it thinks the table is smaller than it is because of the table stats. Or sometimes I've just seen this, it's just doing weird things. For some reason, you know, the logic built into the query planner is just ignoring an index to be making the request significantly faster. In some databases I've worked in, you can hint at the query planner. So you can tell something like, use this index for this query. Other databases like Postgres don't let you do that. One of the things that's particularly tricky about this too, is that because the query plan is dependent on the state of the database, you can look at the query plan that you're getting in dev or in staging, and then the query plan that actually ends up running in production can be completely different. So it's just something to be very wary of, that if there's a request, it seems like it should be fast. Like you've got it indexed, you've done the best practices, and it's just going way slower. It might just be because the actual query plan that's being used in production is non-ideal. Counts aren't cheap. This is maybe more of a novice kind of scaling tip, but I came from a Rails world, and all over the place in Rails code bases I've worked on, one of the really common things we do is we do some type of count to see if there were rows to render, you know, like in HTML in a template or something, rather than fetching the actual data, based on the logic that counts would be cheap. And it seems like it should be cheap. You know, oh, I just want to know how many rows are in this table. You know, the database should be able to tell me that without breaking a sweat. In many cases, counts will be as expensive as the actual query. So especially if you're going to do a count to decide whether you're going to fetch the actual full data set, a lot of the time you might as well fetch the old data set rather than doing a count in the first place. Like again, going back to the query plans, if you look at the query plan for how it's going to evaluate a count, it's very similar to how it will actually just query all the data. One caveat for this is that depending on the engine, I was just talking about table stats, in some databases you can actually query the table stats. Now, those numbers aren't going to be accurate, but if all you care about is approximate number, say you have some vanity metric about your number of users on your website, you don't care if it's perfectly accurate and up to date. Querying those table stats can be a good option to get a very cheap, fast query like a count, but that actually isn't doing the count operation. Again, this will depend on the database engine. Some databases, this might not be the case. Okay, strive on homogeneous load for individual pieces of infrastructure. So that's a bit of word salad, but basically the idea of this is that imagine you've got checkout lanes in a grocery store. So you've got one lane here and another lane here, and then you've got people waiting. So what they'll do in grocery stores is make an express lane. So we'll say this lane is, less than 10 items. And the advantage of this in the grocery store context is that for the people that aren't asking as much of the quote unquote checkout system, they don't have to wait as long. So, if you're just, running in to grab milk, you can get in and out. If someone's coming in to do their major grocery shop for a month and they've got tons of groceries, they'll be put in another lane. And the idea is that the people who are just coming in quick and doing small jobs, they, first of all, benefit more in terms of the percentage of time of their shop, their visit, because their visit is shorter, their checkout time is also shorter. So, and to give you a server context, this would be like if you've got 100 millisecond overhead in a proxy layer in front of your servers, and someone comes in with a 10 millisecond request, that 100 millisecond overhead has 10x the request time. Where if someone's doing a really slow request that takes 300 milliseconds to process, that 100 milliseconds is a smaller percentage penalty on the overall request time. So that's one of the ideas of this type of architecture is like you've got a fast lane, you've got a slow lane. Maybe the slow lane is for things like reporting queries, big admin reports, things like that. And the fast lane is just the API queries driving the usage in the actual client application. You want that usage to be really quick, but people running a big report, understand they might need to wait 3 seconds for that report to render. You don't want that 3-second report making everyone just trying to use the app get put in behind it in queue, have to wait 3 seconds for that to flow through. So that's one of the reasons. The other reason for this is that if you start to try and segment your infrastructure so that each piece of infrastructure has more consistent, homogeneous hits on it, it is far easier to scale. It's often easier to tune, because you're dealing with more just consistency in terms of the load that's hitting it. And often it's more predictable to scale as well. So something like the reports, well, maybe those all land at, within 2 days or 3 days around the end of the month, because everyone's running their end of month reports. So then you've got a separate lane of infrastructure and you can scale just that infrastructure while understanding that your fast lane doesn't need to change. So it gives you more control over scaling your infrastructure in a more targeted way for the elements of your system that actually need it. And it also makes it way easier to understand the performance of your system. If every request is similar, then you're not drowning in this question of like, my memory is bloating, where the heck is this coming from? There's all these different types of requests hitting it. Which ones of these requests is causing all this memory bloat? Your fast lane is probably not going to be seeing that memory bloat, whereas like your slow lane, you might just be assuming that you run less threads on that server, knowing that the memory is going to bloat more. So it's you can configure it more specifically to be more fine-tuned to the type of load that it's going to experience. So there's other places where this impacts. So things like, I'm a big believer, if you're architecting API, how can you make every API request perform similarly? So make every API request take 50 milliseconds. To make every API request take 100 milliseconds. And that can be counterintuitive, but again, it makes it way easier for your system to scale, makes it more consistent for your users. There's a lot of benefits to it. So things like pagination on large requests with thousands of results is a good idea. And then looking for opportunities where you can actually, if there's an opportunity to improve the performance for the large requests at the expense of the faster, smaller requests, I look for those opportunities to pull things together, even if on net it's going to increase CPU time, memory usage, etc. Because again, it's pulling things towards a more consistent, homogeneous state. So it's one of my beliefs. And then this is the last rule, and one that I think is pretty important, is I come from the startup world, and I've gone from the scrappy, starting from scratch up to internet scale. And I've also mentored a lot of startups. I've worked with a lot of startups in a professional capacity. One of the most pervasive ideas that's out there, and it comes both from the business side and from the engineering side, is, oh, we'll fix our scaling issues later. Later we'll hire someone to fix those problems for us. This never happens. You are never in a position where it's like, oh, we've got so much money coming in. Let's allocate, a head count of 5 people just to be proactive about scaling issues or to go pay down our scaling debt. The main time that you're going to fix scaling issues is when something has broken and sales is breathing down your neck, everything's a dumpster fire. If that's the type of mentality. If you're waiting for a time when it will feel like you have the resources to go fix these things, it's never going to happen. And the only time you're going to be fixing these things is when they're kicking you in the teeth. So this is a very convenient fallacy to believe that at some point in the future, you're going to have all these resources that can just deal with these problems for you. And this can be particularly nasty because if you have 10 years worth of customer data in your database now, to go and fix an issue with your data schema that's going to prevent you from scaling is going to be way, way, way harder. This isn't true for everything. I'm certainly not advocating that you need to architect everything from scale, but looking at decisions you're making early on with the lens of how hard would this be to change later is an important lens when you're thinking about some of these scaling issues. So, don't worry about hand tuning your database queries, making sure they're optimized. But like looking at things like creating a table that is going to be very large, is going to have very high churn, is probably going to become problematic at some point because of some of the things I talked about earlier. So again, don't over-engineer, don't over-architect your systems early, but don't wait for a time in which you feel like you have the resources, because it's never going to happen. So lastly, just wanted to say, thanks if you're still here. Thanks for listening to my points. If you've got any questions, probably your best bet's to email. You can email me at ben@parakeeto.com. Parakeeto is my current company that I'm working on. We do business intelligence off of time tracking data for agencies. So if that sounds like something that might apply to you or someone you know, get them to go check out our website. And you can also hit me up on Twitter at Ben Zitlau. Email's probably your best bet to get a response. So thanks a lot for listening. I hope you found it useful.